check if it works at all, not for providing predictive results. Maybe just strengths of field to new images and
I put it at about 1,000 times small.
yeah, and it's still diverse.
Yeah, because right now what I just figured out, you know, how can I get it safely below the threshold where VAS will complain about it, just in case that's causing any issues. Yeah, I don't know, trying stuff, but. But with what I have calculated, I mean, that's like completely useless. Because like it doesn't, the band gap and everything like hardly changes at all with an electric field with what I'm currently doing. Yeah, so the MATLAB code and VAS are both in electron volts range. Okay, I guess I could. But like even. Yeah, but I mean, even with changing the, so I have like, you know, positive and negative electric fields with the values that we originally were looking at, and then I reduced the electric field by quite a bit. You know, the gas would quit complaining, and I got those optimized against numbers, no change really in the States. I mean, they do like, you know, some get like switched around in which order, you know, there's like little shifts here and there, but I mean, that's.
homeworks to collect. So please try to send them by email if, or whatever, or submit maybe.
Is this
The original one that we discussed before.
oh, the lab one?
Yes.
Can we turn that in tomorrow or today?
Well, today is better because, well, I don't care, you can do it tomorrow, but tomorrow you will be busy preparing for presentations.
Okay.
I thought the lab ones were due on the lab day.
No, it's in class. Okay, well, thank you for coming and keeping support of the of this class. So we are in the computational chemistry class. We have successfully separated electrons and nucleus in previous month, in previous chapter, and most of the time right now we are not looking onto geometry optimization, although all of you are certified experts in geometry optimization, you know how the algorithm is working. Now we are starting electronic structure when ions are nailed and are not moved, right? And we do need total energy of all electrons together. This is the I wouldn't say the simplest, but it is background theory for all other computational methods. So some of them can be formulated simpler, but it is starting point for everything. And we are going through this theory slowly but surely. Oh, all together, thank you. So, thank you for submitting the homeworks. So this theory has, as you will see on the printouts, and you did it in one of the previous homeworks. You summarized Hartley-Fock theory in a couple of lines in your answers. So it is not as complicated if you already know what you're talking about to formulate and let other people recognize that you are aware of it. But there is a big danger to miss some concepts. Even if you write equations, there are several background concepts. So it's it is possible to express shortly, but we are analyzing it for a month to make sure that we are not missing important background concepts. And among them, we already covered Slater determinant and spin, which I think you did successfully in your homework. And we discussed the idea of the ionization of a molecule and then subsequently putting electrons back with understanding that mass, the amount, the majority of electrons form additional interaction, additional force on the last electron that we submit, the background field, right? And so all of these concepts need to be together. And last time we briefly covered variational principle, and we reviewed the concept of molecular orbitals, right? So we will look more tightly on the way how the influence of background distribution of electrons affect the last electron. And it will be very similar to last 10 minutes of our previous meeting, if you were watching it live or in recording. So as soon as we declare one electron Fock operator, the electron details of electron interaction, we will be ready to go into self-consistent equations that are being solved in Fock. Just because of the time limitations, we need to set up your presentations on coming Thursday, and then on the next week we will start new software. We will be done with Gaussian. So next week there will be last lecture on Hartree-Fock theory, and the one number 16 will be kind of a bridge between molecules and solids, so between Hartree-Fock theory and the so-called density functional theory. But in 2 weeks we will go to main part of the main material of the course that will make you very able, independent researchers in material science, computational chemistry, and physics. Okay. Please feel free to stop me any time. So here are your votes. I don't remember if I've heard back from Kurt, so I put you on number 11. So share experience how you run Gaussian on CCAST. And probably I'll put you at the very beginning, or like second or third. Okay? So if you have corrections, let me know. And I've sent them notes. You should see these things. So if I immediately go to material assigned for today, it will be so quick that you will not realize that meeting is over. So just few time with review what we did before, if you don't mind. So the we are looking to solve electronic part of molecular Schrödinger equation, right? And we realized that it's too complicated. So we need to compose multi-electron wave function, not because we want it. It is because nothing else is possible with today's facilities as product of one electronic or wave functions. And to match the anti-symmetry relation, one needs to, instead of simple product, one needs to do Slater determinant. So in this little chart, which can be which is a little ugly, so we got a spin Slater determinant, concept of mean field. Well, correlation should, there is a Coulomb. Correlation will be covered in density function. Variation of theorem, yes. And here we do Coulomb exchange today. And as soon as we are ready, there will be last part will be self-consistent cycle to find orbitals and total energy. In some sense, I hope to cover again in this review the search of minimal total energy of electronic system is analogous to search of the minimum of potential energy surface for geometry. But when you find best optimal geometry, you vary interatomic distances, right? And if you find electronic structure, you vary expansion coefficients in front of atomic orbitals. So you change orbitals that enter into wave function until you arrive into minimum of energy. So there are additional variables that you slightly tune until you come to the minimum. But those variables are not geometrical Cartesian space. determinant. Concept of background. So if the red is original electron, then the second electron comes to the spots which were not occupied because of repulsion. And it is your favorite term, right? Expectation value. So while deriving equations appropriate for particle theory, we did a trick. We looked for Hamiltonian that depends on all electrons and took expectation value in respect to partial wave function of the second electron. And then the resulting object is neither operator for all electrons nor a number nor an energy for everything. It is partial operator, partially a number. And when we did it, we arrived to, well, we do everything in oversimplified way for one of the two electrons. Otherwise, it will be several of those equations. So those are equations for first electron that includes, that is formulated very similar to Schrödinger equation, okay, with the difference that in Schrödinger equation one has only kinetic energy and attraction of the first electron to like attractive sites, nuclei. And here this is the Fock operator, which includes additional term that corresponds to Coulomb interaction between our electron in the unknown orbital with second electron, and generally there should be a sum over all but one electrons with the background distribution of the remaining electrons. So these curly brackets are referred to with letter F, Fock orbital. And if you do it for the second electron, assuming that the first one is already known, you see that functional form is the same. So in fact, this two equations are the same. They just, as standard partial differential equations, they generate several answers. And then we ask the question, in which functional form we will solve these equations, right? Because if you are exposed to differential equations, you know that it's a big headache. The best way to solve differential equations is assume functional form of the solution with unknown coefficients and then just find coefficients. And the idea that we practice here was to search for this unknown one electron wave functions as superpositions of atomic orbitals on each atoms that are present in the molecule. So this those are 4 quantum numbers, and these atomic orbitals are centered around each ion. And this expansion coefficients is what we need to find. So we solve Fock equation in order to find this expansion coefficient C. So I'm jumping a couple of slides back. And why do we need variation in principle? Because we need criteria. If you develop a procedure to solve for this total multi-electron wave function, for total energy and for orbitals, we need a criterion, since it all will be done numerically. We need a criterion to say whether our solution is good enough. And there is a theorem that if we deviate from ground state to some non-ground state, energy will be always bigger. And this formulation is needed. Do I have this slide? No, I do not. Okay. I will verbalize it. So this is needed for comparing total energy of the current version of the wave function, total energy for trial wave function, and checking if it approaches some asymptotic value. So if we will try different delta psi, evaluate energy of the resulting function and see if it gets smaller, approaching to the same value, it will be a good sign. So it is the reason why we need this variational theorem, which is like the okay, and 2 meetings ago we agreed that in this connection, in this streamline from atomic coordinates to total energy, there are atomic orbitals, there are absolutely correct wave function, there are molecular orbitals and expansion coefficients. So the only thing that we can tweak, we can tune, are expansion coefficients of molecular orbitals over atomic orbitals. So we do need equation to find this C sub j and this superscript for atomic quantum numbers. Good. And the last thing we did before the beacon, the slides were prepared in South Dakota. Therefore, everyone was so enthusiastic about seeing SD abbreviation. But here it stands for Slater determinant, right? So there is a need to take into account electron-electron interaction. This is really a challenging thing. It creates challenges and complications all the time. And we cannot give up the antisymmetry of electronic wave function. Therefore, we are using Slater determinant. And if we are using Slater determinant, then contribution to the energy, to the total energy from electron-electron interaction is formulated as Slater determinant on the left, Slater determinant on the right, and electron-electron interaction in the middle, right? If you have more than 2 electrons, it will be summation, right? So let's repeat what we did last time. So there is one bracket with 2 terms. First term, second term. There is a second bracket with 2 terms. First term, second term. And then we multiply, and there is like this 1 over delta R in the middle. If we open the brackets, here are the brackets and here are the brackets. How many terms will be total? 2 times 2, 4, right? And if we will look on these 4 terms, there will be 2 pairs. So first pair, when index of molecular orbital and number of electron coincide, orbital 2, electron 2. Orbital 1, electron 1, orbital 2, electron 2. So when the indices will be repeating in the bra part and in the cat part. by the way, if we process this bra and this cat, it will be the same. It will be equivalent as if you would just rename variables. And here you see that minus by minus will be plus. So there will be one type of terms with positive sign, which corresponds to repulsion, and it will correspond to keeping the order of indices the same. And then there will be cross terms, where negative is multiplied by positive, or positive multiplied by negative, where the order of the indices is swapped. So 1, 2 changes to 1, 1 changes to 1, 2, and 2, 2 changes to 2, 1. Right? So the swapped terms will have negative index. So what does it mean if the energy is negative? Attraction. Or if we are chemical chemists, we can tell stabilization. Right? So negative energy means something is stable. It's more like energy on a couch is lower than energy on whatever weather stairs, or when you sit on the roof. And this is an important fact that describes why Hartree-Fock theory, it's not ideal, it gives big errors, but it is reasonable qualitatively. So positive is Coulombic repulsion, and negative term is a counterintuitive thing that is not available in classical picture. So because of swapping of the order of electrons, there is additional factor that makes electronic system stable. So although electrons are expected to repel each other, there is a portion of electron-electron interactions that corresponds to attraction. And it is referred to as the word exchange. Okay. So now, how much time did we spend? Okay, so now there will be something that I anticipate to be very quick. Two terms. One, when they coincide, molecular orbital 1, electron 1, molecular orbital 2, electron 2. Right? Positive term and negative term. So, would you like to, Nathan, would you like to go and explain what these drawings are?
Is that like?
Please try it. Try to point by fingers and explain your vision.
Well, I'm not 100% sure.
Just try it. It will be.
Like, it looks like you're modeling the position of 2 electrons. And then there's this, like, this curly thing is a spring. So you're just saying that the force between them is like a spring that can oscillate. Is that what you're doing?
Okay, and what are other labels?
The phi, just the orbitals for each electron. And they're
Okay, and
conjugates.
why there are 4 arrows?
Well, there's the orbital for 1 electron, the orbital for the second electron, and then there's the conjugates for both.
Okay, and how would you direct the time? Where is the time goes?
Well, this way for the real one, and then this way for the, or not real, this way for the
Okay.
regular wave function, and then this way for the conjugate.
Thank you. Thank you. Does it make sense what Nathan explained? Anyone wants to correct him? There were no big fails. Generally, it's correct. So, if you are, well, most of us are in material science, but some of us are in physics, right? And there is experimental physics, and there is a, well, we are doing computation, but there is a theoretical. Means people are paid to derive equations and write many lines of equations. So major feature of a human being is laziness, right? Nothing wrong with it. So imagine if you have complicated molecular electronic system that you need to describe with equations. And suppose that you have computers. Then you need to carefully evaluate terms in the interaction. And you need to write equations like this again and again for different orbitals, different electrons. There will be additional things. And writing is boring and exhausting. So there was a person who designed a standard way how to convert writing into kindergarten level figures. So he got Nobel Prize. Well, not only for this diagrams, for other things as well, but and his who knows the name? Yes. Okay. So the straight line means electron in state which is labeled here, right? And the wavy line means interaction. So it interacts with something. So the electron in the orbital 1, time is typically oriented up for all. So propagates, and then it experiencing repulsion from the second electron. So repulsion is can be assumed that it is not continuous, but well, here it doesn't matter, but just for again, not to tell in public, but only between us. It can be considered as collision of billiard balls. So it just flies, they kick each other and then move in different directions. Okay? So here we do not care about change in the quantum state. You see, it was in state 1 and it remains in state 1. So probably interaction was not so strong. But here we just do very basic abstract diagram. So the electron in state 1 slightly interacted with electron in state 2. And interaction happened when electron was in space position 1 and electron 2 was in space position 2. So intuitively it looks like they just collide and repel, right? So when you see such abbreviation, it means the same as this Coulomb attraction term. Positive. Now, I don't know how to move this arrow away, but here is only phi 2 and arrow up. So can we, and this is very intuitive, can we do similar diagram for the counterintuitive attractive term when two electrons, like two billiard balls, interact with each other, instead of repelling they kind of stick to each other, stabilizing term. So this can be, if one tries to convert this equation into that diagram, it will be somewhat possible if instead of repelling they pass through each other, right? So the number 2 went through and went this direction, number 1 passed through and went to other direction. But if we are looking only on the left part of the diagram, what do we see? So we do an experiment. We submit electron in quantum state 1, and when it was in the space region 1, due to interaction, it suddenly changed its state and converted into state 2. And it can be interpreted that electrons 1 and 2 swapped their quantum states, exchanged quantum state. And this diagram is corresponding to exchange attractive interaction. So here the solid, the lines, straight lines do not cross each other, and here they cross. So if you will decide to give up experiment and computation and go to theory, then there is a high chance that you will draw 200 of such diagrams per day. And then convert like a dictionary from equation to diagrams, and then from diagrams back to equations. It's like oversimplified description of what theorists are doing. Yes?
So all these pictures are basically a pictorial like representation of the like expectation value of the electron-electron repulsion.
Electron interaction, yes.
Okay.
There are additional pictorial representations for other things that happen in the universe,
Okay.
like interaction with photon, scattering of energy, dissipating energy into heat. And it is especially like we are lucky in this class because we are doing simple things from point of view of a theorist. So we have only nuclei that are positively charged and electrons which are negatively charged. That's it. Two types of particles where nuclei can be a little heavier for different atoms. There are areas of science with much larger number of particles, and each of them will have different arrows. They will interact, and the computation as we do in the with good basis function is not possible there. It's much more complicated thing.
So the inner arrows mean psi 1 and psi 2 are like interacting via the electron-electron potential, and then the out arrows means basically signifies what happens to psi 1 and psi 2 after they've like interacted with that potential.
Yes.
Okay.
Yes. But it's not external potential. They create potential for each other.
Okay.
What else? Okay. So there will be few figures more. So few equations. Remember what are we doing? We do not want to solve actual multi-electron equations because of computational hardness of things. We do want to solve only one electron equations, if possible, even if we need to pay price for it. But electron-electron interaction, by its nature, it's interaction between two electrons, right? So the Coulomb electrostatic interaction is a bad guy, right? Because we cannot do our favorite one-electron problems with it. So what if we do a little heresy and make a Coulomb operator that will be only acting on one electron? Okay, so this is the main part of the Hawk theorem. We already described it in 2 lectures ago. We will do it once again. So we do practice expectation value of Hamiltonian Coulomb interaction in respect to one electron, and we keep it still as an operator in respect to another electron. So partial contraction, partial expectation value. So if our wave function is like product of two one electron wave functions, and we split the contraction, the integration over first electron and second electron as two independent procedures. So if we remember on previous slides, we were doing two integrations over R1 and R2. Now let's do integration on R2 first and postpone second integration for a later time. So we are keeping the 1 over delta R in the denominator, and we put the probability distribution for second electron, which is in the second quantum state, in the denominator, right? And we are integrating over the position of second electron. But this will be not a number, so we integrate our dependence on R2, but this object will be still depending on R1, right? And if we want to convert this hybrid operator into a number, we need to integrate it over phi sub 1 as a function of electron 1. Right? So if you would plug this expression here, you would recover back an integration over R1 and R2, as we did for SD, Slater determinant, to get Coulomb interaction. But we intentionally want to split these two operations. So if we complete this integration and we do not complete this integration, then this will be a unique object. Instead of acting on two electrons as normal Coulomb interaction does, this object will act only on one electron, on R1. Okay? So we partially integrate over position of second electron and keep, so this object keep the operatorial nature in respect to the first electron. Briefly, people call it Coulomb. So it's a repulsive influence of second electron onto the first electron. If we put here different orbitals and we still integrate over R2, then it will be a thing that will give rise to the stabilizing exchange term in the total energy. And again, this is partial orbital, partial operator that acts on electron 1. Stop me and ask questions, even if you know that it will be not part of homework, because it is like challenging things, and anything we do after will build on this. Okay. Now, if we do have the same orbital, same argument, if we do have this Coulomb term acting on the first electron in state 1, right? Can we represent it on a diagram? Like the original diagram for Coulomb interaction, it was like a little bug with 4 legs, right? But here we do integrate everything that relates to position R2 and everything which relates to quantum state 2, second electron in state 2. So guess how the diagram will change if we perform this integration. Try to be creative and use your imagination. Yes?
Would we just erase the 2 back legs then?
Yes, or put a black box or a ball instead of that. So in some sense, the second electron acts as a wall. So the first electron will scatter from this wall, right? And then a wall, a potential, it will be one electron potential. Coming back to introductory quantum theory where everything is easy to solve. So no second electron, just a potential that acts on the first electron. And if you try to do it as in pictures, you can just put a black box and first electron will smash into this wall, right? So it is one electron potential that carries average information about all electrons except our electron number 1 at position 1. And this is, again, intuitive. It just hits the wall and reflects from it because it is repulsive, right? So if we do the same procedure, oh, by the way, product of this R2 in state 2 star state 2, it's either probability that second electron in quantum state 2 is residing here, or density, right? Square of the orbital is density. Okay, if we try to repeat the same procedure for exchange diagram, we again can put a box here, right? But as a result, it will look like we were acting on electron in quantum state 1, but due to this nature of this exchange term, it suddenly became the electron in quantum state 2. So the index of quantum state exchanged. So it's like if you imagine me taking accelerating and smashing into a wall, I probably will reflect back. And now assume that I accelerate, smash into the wall, and suddenly instead of me, it will be Dr. Krzyzewski. Exchange. And this will be like negative energy, favorable situation, if you would be electrons. Good? Maybe one more piece of information that will make you comfortable in reading the handouts. So, again, everything is about wavelengths. The Coulomb diagrams were, Feynman diagrams were for physicists. But theoretical chemists also need to write a lot of Coulomb interaction, and they kind of developed independently and created their own abbreviations. So instead of diagrams, there is a frequent notation to just count the index of quantum state, right, in each orbital that contributes to Coulomb interaction. And Coulomb interaction always has 4 wave functions, right? And often, we will not speak a lot about it, but we do need interaction between molecular orbitals. But each molecular orbital is a superposition of atomic orbitals. Therefore, one can compute once Coulomb terms, Coulombic interactions between all atomic orbitals, and then just have them as a table and collect them with the right expansion coefficients. Okay? So there are different possibilities of orbitals used in this 4-wave functions, or two electron integrals. And one can just take the indices and assume that there are only 2 variables that will be integrated anyway. And then one puts it as round brackets with a vertical line in between. So first, second, third, fourth. RSTU. Okay? Then if first two indices coincide and second two indices coincide, like 1, 1 and 2, 2, it will, this expression will bring us repulsive Coulomb term, right? That is intuitive. If one has first and third coincide, and then second and fourth, first and fourth and second and third coincide, then it will be exchange. I'm not a big fan of this language. I'm not using it every day, but if you look through some textbooks that were originating from computational chemistry community, they will not like write integrals. They will immediately use these notations and assume that reader is well versed in them. So if you browse this little handout, I'll give you an example.
So the top one is propulsion, the other one is attraction.
Yes. Repulsion and stabilization. So let's look on equation 10.20. It doesn't copyright today, unfortunately. Okay. I was trying to project it, but did you found it, right? So after the diagram, and it does show the formulation of Fock matrix, of Fock operator of it has the H, which is kinetic energy and interaction with nuclei, and then a double summation, and then bracket that includes Coulomb and exchange. They're going too far, and it should be a little simpler. Indices should coincide here. So, but other than that, it is a good reference. Okay. So, if we do want to formulate one electronic equations for molecular orbitals that will carry on interaction with the rest of electrons, one would put Hamiltonian H, which will include kinetic energy and interaction with nuclei, and Coulomb and exchange term with Coulomb positive, repulsive, and exchange negative, attractive, that will make summation over all electrons. And here should be n minus 1, all but 1 electrons, so to avoid interaction of electron with itself. So I believe that it will be, we can chat a little bit more, but for major information it will be sufficient for today. So let's focus on presentations and practical aspects of using Gaussian and Gauss view. But when we will meet next time for like academic lecture on next Tuesday, we will start from this point and describe two things. First, how to solve for expansion coefficient C that connect atomic orbitals and molecular orbitals. And this will be solved in the iterative, self-consistent manner. There is another thing, I'm giving just a little heads up, that the set of coefficients that we need to find can be written in a matrix form, right? Just as a vector column. Then each of these operators will be matrices, and the Fock equation for orbitals will be represented as eigenvalue problem for a matrix, in matrix form. So we'll do two things next Tuesday. Matrix form of Fock equation and self-consistent procedure where the output of this molecular orbital will feed into reformulating this Coulomb and exchange terms and then resolving it once again until things converge. Okay, I think, let me double check. Yes, it's my, we are done with lucky number 13. Done. So I'll stay here to answer any questions, but formal part of the meeting is done. Yes?
Well, I have a question.
Please. Is it about class or general? More questions about class material? No? Okay. So then see you tomorrow at when? 5?
5, yeah.
And again, tomorrow at midnight I will expect some PowerPoints. Oh, let's sit and do it together.